Okay, so that brings us to Newton's binomial theorem. So remember, the binomial theorem says 1 plus x to the n is this polynomial, summation n choose k, x to the k. And I'm just going to write this out to remind you. It's 1 plus n times x plus n minus 1 over 2, x squared, and so on all the way up to x to the n. In particular, it's a polynomial. It's finite. It only has a finite number of terms. Now, what if I asked about 1 plus x to the r, where r is a real number, but not necessarily an integer? Is it possible that this formula holds? So you'd have something like this: summation r choose k, x to the k, k running from 0 to, well, to what? I'm not sure. Is it possible that such a formula could be true? Well, let's look at an example. Let's take r is equal to a half, so you're looking at 1 plus x to the 1/2, which is to say the square root of 1 plus x. Now, of course, this is not a polynomial, so it can't have a finite number of terms. But what I'm hoping is that there's some formula like this, and, well, the only possible thing that could be true would be to make it a power series. It's got to be an infinite sum. And it turns out, remarkably, that this is true. So, here it is. Here's Newton's binomial theorem. Suppose you take the function 1 plus x to the r, where r is an arbitrary real number. The formula says this is the infinite power series, summation k running from 0 to infinity of r choose k, x to the k. And notice the powers of x on the right hand side are all integers. There's nothing involving r over there. It's these are just integral powers of x. Here r is a real number. And now there's one crucial thing here. This only makes sense for absolute value of x less than 1. Unlike the binomial theorem, this is an infinite power series, and you need to get into some analysis and calculus and convergence and all of that stuff. And the statement is that if absolute value of x is less than 1, then the right-hand side converges absolutely to the value on the left-hand side. So when you talk about infinite power series, you got to be really careful about convergence and what kind of convergence you have and so on. So I'll come back to that. So let's prove this theorem. Well, this is just the Taylor series of 1 plus x to the r around x is equal to 0. So I'm saying that if you take the function f of x is 1 plus x to the r, this has an infinite power series expansion, the kth derivative of f at 0 over k factorial times x to the k. That's the Taylor series. And what is f to the k of x? Well, it's r times r minus 1 times dot 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 k terms r minus k plus 1 times 1 plus x to the r minus k. And when you plug in 0, you just get this thing, r to the k falling. This is these k terms like this. And the last term is 1. And you just plug that in, and you get the formula. You get r times those k terms divided by k factorial times x to the k. And, well, I'm skipping over proving that it's absolutely convergence, but that's actually quite easy. So let's take the case r is equal to minus 1. You get this weird looking formula. 1 plus x to the minus 1 is equal to minus 1 choose k, x to the k. Well, what on earth is minus 1 choose k? Well, it's minus 1 times minus 2 times dot 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 minus 3 times dot 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 minus 1 minus k plus 1. That's k terms going down from minus 1 divided by k factorial. Well, let's see. What is that? there's a bunch of minus signs in there. There are k terms, and every one of them, if you multiply every one of them by minus 1 to change the sign, what you get is minus 1 to the k times 1, 2, 3, dot, 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 up to what? Up to k terms. And the whole thing's divided by k factorial. And lo and behold, the k factorials cancel, and you just get minus 1 to the k. So in this case, Newton's binomial theorem says that 1 plus x to the minus 1 is equal to summation, k running from 0 to infinity, minus 1 to the k, x to the k. Huh. That's interesting. Well, let's see. One nice thing to do is to replace x with minus x, and then on the right-hand side, well, the left-hand side is 1 over 1 minus x, and the right-hand side becomes minus 1 to the k minus x to the k, and the minus 1's cancel, and you conclude that you get the following formula: 1 over 1 minus x, that's the left-hand side, is summation, k runs from 0 to infinity, of x to the k. So that's a classic formula. It's true, and it's quite a useful one. So let's look at it a little bit more. And again, this makes sense for absolute value of x less than 1. So let's do an example. What if I took x is equal to a half? What does this say? This says 1 over 1 minus a half is equal to, let's see, 1 half to the 0 plus 1 half to the 1 plus 1 half squared, and so on, which is 1 plus a half plus a fourth plus an eighth plus a 16th, and so on. And let's see, this side is 1 over a half, which is 2. So I'm claiming that 2 is equal to 1 plus a half plus a fourth plus an eighth, and so on. And absolutely, that's true. You can even see it. You draw the picture. Here's 1, and then 1 plus a half, and then 1 plus a half plus a fourth. You're getting closer and closer to 2. So it's a strange looking formula, but at the end of the day, it's actually quite natural and correct. Here's another way to see this formula. I'm claiming that 1 over 1 minus x is this infinite sum. So let's multiply both sides of this equation by 1 minus x. So I'm claiming that 1 is equal to 1 minus x times this infinite power series. And let's multiply the right-hand side out. What do you get? You get, let's see, you multiply 1 by 1, you get 1. And then you multiply here, you get minus x, and then 1 by x gives you an x, and then minus x squared, and then you get a plus x squared, and you get a minus x cubed, and so on. It's the famous telescoping series. All of the terms cancel out pairwise. 1 minus x plus x minus x squared plus x squared, and so on. All of that equals 1. Now, I need to say this is a huge cheat. This is a formal calculation, and it's not really literally correct. For example, if x is equal to 2, it's certainly not correct that 1 over 1 minus 2 is 1 plus 2 plus 4, and so on. So this calculation that I did is formally kind of nice, but definitely is not to be counted on, and it's definitely not a proof of the formula. I should say, with a little extra work, it can be made into a proof, but I'm not going to do that here. Okay, so here's one last application of all of this. Let's take r is equal to minus n, where n is a positive integer. So this says 1 over 1 plus x to the r is 1 plus x to the minus n is 1 over 1 plus x to the n. And so the formula says that 1 over 1 plus x to the n is equal to summation minus n choose k times x to the k. So this is a generalization of the previous one where I took n is equal to 1. And, well, something very similar happens here. What is minus n choose k? Well, let's write it out. Minus n choose k is minus n minus 1, and so on, k terms, divided by k factorial. And just like before, you write that as minus 1 to the k times n plus 1 up to, let's see, n plus k minus 1 all over k factorial. And the right-hand side here is what? It's minus 1 to the k times n plus k minus 1 choose k. And that's a little bit more, that's a sort of more natural looking formula. So anyway, so the formula is that 1 over 1 plus x to the n is this summation minus 1 to the k, n plus k minus 1, choose k, x to the k. And remember, this is an infinite power series as x goes from 0 to infinity. So this is quite a nice combinatorial formula. I'm going to come back and talk about that a little bit more later in the course. All right, there's one last topic I'm going to cover in this video, and that's the multinomial coefficients, which is a generalization, naturally, of binomial coefficients. So remember, the binomial coefficients are the following. X plus y to the n is summation n choose k, x to the k, y to the n minus k. And the generalization of that is, instead of two variables, to have r variables. What is x1 plus dot 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 xr to the n? Well, let's just get a rough idea. It's some sort of polynomial in r variables. And so there's some kind of coefficient, and then there's various powers of the xi's. Call them a1 through ar. And the one thing you know is that the summation of the ai's is equal to n. So there's some sort of sum like this, and the question is, what is the coefficient? So here it is. This is called the multinomial coefficient. It's defined as follows. So we have some integer n, bigger than 1, and some other integer r. That's the number of variables. And we define, we're also given some integers n1 through nr, r of them, which add up to n. Then we define n with n1 through nr down here in the denominator. Not denominator exactly, but the bottom is, by definition, n factorial over n1 factorial times n2 factorial up to nr factorial. Okay? So that's, by definition, a multinomial coefficient. And it's defined again for any integer n, and then the integers in the bottom have to add up to n. Okay, so let's look at an example. If you take r is equal to 2, that is to say we write n as n1 plus n2, so n over n1, n2 is this number. And, well, let's see, obviously this is n factorial over n1 factorial, and then n2 is n minus n1 because they add up to n. And so this is just n mod n1, or excuse me, n choose n1, or equivalently n choose n2. So in the case of r is equal to 2, you're getting the ordinary binomial coefficients. The only difference is, for the binomial coefficients, you only write one of the numbers in the bottom instead of both of them. And here's the theorem. If you take the polynomial x1 up to xr, some of those variables, and raise it to the n, what you get is summation with the multinomial coefficients, x1 to the n1 dot 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 times x2 to the n2 up to xr to the nr. And what is the sum over? Well, I'm going to write it like this. It's the vector n. And what this means is the vector n is this r tuple n1 through nr, where they add up to n. And they're all non-negative integers, bigger than or equal to 0. So let's look at the proof. Of course, it's very similar to the proof of the binomial theorem. So you just take this thing, x1 up to xr to the n, and write it out. It's the sum of the variables multiplied times itself, n times. And now you just multiply this out and you get a gazillion terms, and you have to group them. And what does it look like? Well, really the main question is, what is the coefficient of a particular term, x1 to the n1 up to xr to the nr? In other words, when you multiply this thing out, how many times are you going to get this particular term? Well, when you multiply this out from each set of parentheses, you have to choose one of the variables. And in order to get this term, you have to choose x1 n1 times. And there are choose n1 ways to do that. There are choose n1 ways of getting that term. And now, how are you going to get x2 to the n2? Well, you have to choose n2 you have to choose x2 n2 times from what's left over, which is n minus n1, choose n2. So that is to say, it's this number right here. Now, taking both of those into account, it's going to be the product of these two numbers. That's going to account for x1, the x1 and x2 terms. So when you multiply these, what happens? Well, you have this n factorial term here from the first guy. And notice that the n minus n1 factorial here cancels. And so when you multiply them, what you get is n factorial over n1 factorial, n2 factorial, times what's left over, n minus n1 minus n2. Okay? So now you just keep doing this. For n3, you need n3 choices of x3, and you keep doing that, and you get n3 factorial, n minus n1 minus n2 minus n3 factorial, and so on. And after r minus 1 steps, you get down to here. You get down to n r minus 1 factorial, and then the last term is n minus the sum of the previous ones. And that's it. Now this last term, because the numbers add up to n, is just nr factorial, and that's the formula I was looking for. So you should go back and go through that calculation again, make sure you believe it. So let's do an example. Suppose I asked for the coefficient of x squared y cubed z to the 5th in x plus y plus z to the 10th. Well, that's just a straightforward application of the formula. It's going to be 10 factorial over 2 factorial, 3 factorial, 5 factorial. So here's a question. Suppose I looked at the sum over all of these r tuples, n1 through nr, of the multinomial coefficients. So I'll just write that out. What I mean is the sum over the r tuples n1 through nr of n1 factorial of this quotient. And what is that? What's that sum? Well, that's easy. You're just taking, let's just take x1 through xr equal to 1 in the multinomial theorem. And the left-hand side turns into the sum of the 1's to the n, and the right-hand side is exactly this thing. All of the xi's are 1, so you just get this sum. And the number of 1's is r. So you get this formula, summation of the multinomial coefficients is r to the n. And of course, when r is equal to 2, that's 2 to the n, which is what you get from the binomial, in the case of the binomial coefficients. All right, let's look at these numbers from a couple of different angles. So suppose I give you a bunch of numbers which add up to n, all positive, non-negative integers, of course. And I ask, how many ways can you put n distinct balls, I love the balls in boxes questions, you know, n distinct balls into r distinct boxes, so that box 1 has n1 balls and box 2 has n2 balls and so on, ni balls in box I. I specify the number of balls in each box. Let's see. So here you put your R boxes, label them 1 through R, and you're going to put a certain number of balls in each box. And the balls are distinct, so they're numbered. So let's say you put ball 4 and 2 in the first box and so on. Well, let's see. So the way to think of this is you take your balls, which are numbered, and put them in any order. And there are n factorial ways of doing that, of course. So let's say, for example, you put them in this order. And then you put in the dividers to give the proper number of balls in each box. So in this example, 2 in the first box, 3 in the second, 2 in the next one, and so on. Now, in the first box, you can put them in any order. So there's a 2 factorial there, and a 3 factorial here, and a 2 factorial here, and so on. Within each box, if there are ni in the box, there's an ni factorial. So the total number is n factorial over n1 factorial, n2 factorial, up to nr factorial. Aha, the multinomial coefficient. So that's a combinatorial interpretation of this number. Well, that's kind of nice. So let's do a little wrinkle on this. What's the total number of ways of putting n distinct balls into r distinct boxes? And again, this is part of the 12-fold way. You might want to look it up on the 12-fold way sheet. N distinct balls into r distinct boxes. Well, ball 1, there's r places you can put it. And ball 2, there's r places you can put that. And so on. So the number is r times itself, n times r to the n. So, well, obviously, that's a combinatorial proof of the fact that when you sum up the multinomial coefficients, you get r to the n, because both sides are counting the number of ways of distributing the balls into the boxes. And on the left-hand side, you're counting them up separately for each possible distribution. So, as always, or I shouldn't say always, but as is often the case, there are several different ways of proving these identities. All right, one last thing I'd like to look at is a slightly different interpretation in terms of multisets. So suppose I have a multiset where the first item occurs n1 times and the second item occurs n2 times and so on up to nr times for r. So notice the total number of elements in this set is the sum of the ni's. I'll abbreviate this like as usual, like this. And how many permutations are there of this multiset? Well, it's easy to see. It's the multinomial coefficient, because there are n factorial permutations, but you have to divide by n1 factorial through nr factorial to account for the guys which are the same. So that's yet another combinatorial interpretation of the multinomial coefficients in terms of permutations of a multiset. One final example. How many permutations are there of the letters in Mississippi? Well, let's see. This is a multiset. There are 11 letters, and let's see, how many letters are there? There's I, M, P, and S. I occurs 4 times, M once, S 4 times, and P twice. So the answer is this number right here, which turns out to be, what is it? 34,650. Okay, that's a good place to stop.